Hey, welcome back to your favorite calculus class. We're going to look at implicit differentiation today. Most functions we've dealt with are given explicitly or written as a function of x, right? Now this one is in implicit form, x, y equals 1, right? But you can solve for y and have it in explicit form. Again, so that y is written as a function of x. So this is implicit form, and explicit is y equals 1 over x, or x to the negative 1. And this is the form that we've needed it in order to take our derivative. So we had dy dx is negative 1 x to the negative 1 minus 1 to the negative 2. In other words, negative 1 over x squared. Now the problem is you can't always use this procedure. For example, here we've got, you notice the 2y cubed, you've got the 4y. Like, how are we going to solve for y and have it y as a function of x explicitly? You can't. So what we have to do is we have to do what's called implicit differentiation. Okay, so that means we're still going to take the derivative with respect to x here, and then what we have to do is we got to apply the chain rule. Okay, so for example, this is fine. The derivative with respect to x, see how these variables agree here? So we can just run it, 3x squared, right? Now here, the derivative for y cubed, so what you do is you say, okay, I'm going to run the power rule, 3y squared, but I'm not sure what y is, right? There's nothing it could be solved for where these variables do not agree. And so what we're going to say is we're going to say dy dx, derivative of the inside, if you will, right? Because we're not sure what y is exactly. So we're just tacking on the chain rule. So that, this is like the f prime of g of x. This is the g prime of x, if you will. Because again, we're not quite sure. Variables disagree. We're not sure what y is. Y could be something else. Okay. So derivative of x plus 3y, next one here. So we go ahead, we take the derivative of x. Notice these variables agree. So it's just 1. And then we take the derivative of 3y. So the constant stays there. You take the derivative of y. It's kind of like the derivative of x is 1, right? But then, again, g prime of x, right? So dy dx. This is the chain rule part. The variables disagree. See how the variables disagree? So it's 1 plus 3 dy dx. Okay? And you know what? Before I do this, let me go back to this one here for a minute. Our xy, when we solve this explicitly and ran it, we get negative 1 over x squared. So we can do this in implicit form now. So we have xy equals 1. If we do this implicitly, so implicit differentiation, let's go ahead and do that. You'll notice we can actually end up with the same thing. Alright, derivative of the first, so I take the derivative of x, which is 1, variables agree. Derivative first times the second, plus the first, so I leave the x alone, and I take the derivative of y. Now notice, variables do not agree, right? I'm taking the derivative of y. Derivative of y is 1, but the variables disagree. I got to throw on dy dx, the chain rule there. And then over here I have the derivative of 1, which is 0. Now what I'm going to do is I'm trying to find dy dx, right? I'm trying to find the derivative of y with respect to x here. So I'm going to take this to the other side, negative y, So I have x dy dx equals negative y, and then I'm going to divide by x. Divide by x. Now I know this doesn't look the same right now, but it is because we know xy equals 1. In other words, y is 1 over x. So when I substitute that in for y, substitute that in, this becomes negative 1 over x squared. See that? So we did it. It's obviously easier to do that explicitly, solve for x, and then run the derivative. But you can't do that implicitly, right? So that brings us to, let's go ahead and do this one now. Let's do some more implicit differentiation. So we're going to take the derivative with respect to x here. So variables do not agree, right? So I run the derivative, tack on the chain rule, so dy dx, run the derivative here, 2y to the 1 power, chain rule, minus 5, derivative y is 1, chain rule, variables disagree, minus, take the derivative of negative x squared, so negative 2x, over here we got 0. Now what I'm going to do is I'm going to solve for dy dx. So first I'm going to take over that the 2x to the other side. So I'm going to add 2x. So I've got 2x. And then what I'm going to do is I'm going to take a dy dx out of each of these remaining terms. Dy dx, and I'm left with 3y squared plus 2y minus 5. That equals 2x. And then notice we're trying to solve for dy dx, right? So we're going to get rid of this 3y squared plus 2y minus 5. So dy dx equals 2x over 3y squared plus 2y minus 5. Okay. Well, as it shows here, or talks about here, most of the stuff we dealt with have been able to be expressed explicitly in terms of the variable x. But you know, there's some like this, x cubed plus y cubed minus 9xy that we're going to take a look at equals 0. They can only be expressed implicitly. Now this one we could, but we're gonna examine that as well. And of course, this one's a circle. This also could be defined in terms of two different equations that are explicit. But again, implicit differentiation is oftentimes the easiest way to go with these. Again, I'm going to come back to this. This is called the Fullium curve by Descartes in the 17th century. I'll come back to that, and I'm going to come back to this as well. So number one. All right, let's see if we can find the derivative with respect to x, dy dx, of y squared equaling x. So we're going to run the derivative on both sides. Oops. Variables disagree, so take the derivative. Don't forget the chain rule, so 2y dy dx, right? That's over here, the variables agree, so I just run the derivative. So dy dx is 1 over 2y. Now, I know this one, you can solve this for y, right? And we'd have two equations, square root x plus or minus root x. And then if we ran the derivative, we'd have 1/2 x to the negative 1/2, or 1 over 2 root x, right? And if we ran the derivative here, we have negative 1/2 x to the negative 1/2, or negative 1 over 2 root x. So the interesting thing is, when we did this implicitly, we had this y right here, right? Well, since y squared equals x, y is one of two things. It's either root x or it's negative root x. So this dy dx, which is 1 over 2y, is two things. I could substitute in root x, or I can substitute in negative root x. But notice, same, right? So you could, oh, that's a positive 1 here. You could have it, do it explicitly, in this case, or implicitly. Okay? And let me go back to the picture here. Here's the picture of y squared equals x, right? We have this, here's our picture of that. In other words, the top one is the square root of x, bottom is negative root x, right? If you were to solve for it, put it in explicit form. And then you've got this, here's the derivative, here's the slope of the tangent line, 1 over 2y, in other words, 1 over 2 root x, right? For whatever x you want to plug in. There's the derivative, dy dx, 1 over 2 root x, and so on. Okay? So with implicit differentiation, we differentiate both sides with respect to x, and then treating y as a differentiable function, and then collect the dy dx, solve for the dy dx. Sometimes you'll make a substitution in for y if you can as well. Okay, let's do another one now. Show that the point 2, 4 lies on the curve x cubed plus y cubed minus 9xy. Then find the tangent and normal to the curve there. Okay, so first of all, here's our x, here's our y. If we were to prove it's on the curve, we just plug in our minus 9 times 2 times 4. So we have 8 plus 64 minus 72. And there you go, 72 minus 72 equals 0. So sure enough, yes, it's on the curve. So that point 24 is on the curve. Now find the tangent, so tangent line, and the normal to the curve there. Okay. In fact, let me give you a little picture of this. X cubed plus y cubed minus 9xy. Let me pull this up here. X cubed, whoops, plus y cubed, what was that, minus 9xy equals 0. So here's Descartes' folium. And then, you know what, let me put on there that 0.24, whoops. On the 0.24. Alright, so there's our 0.24. What we're going to do is we're going to find the equation of the tangent line and the normal. In other words, the perpendicular, the line that's perpendicular to the tangent. Okay, sometimes that's called the normal. That's also referred to as the orthogonal. Okay, so let me go back here. Let's go ahead and do the Now we cannot solve for y explicitly, so we're going to have to run the derivative with respect to x here. So 3x squared, variables agree. 3y squared, don't forget chain rule, dy dx. Now I'm going to think about this. This is negative 9x times y. So derivative of negative 9x is negative 9. So derivative of the first times the second plus the first derivative of the second. So that's 1. Derivative of y is 1. dy dx. And this equals derivative 0. Derivative of 0 is 0. So we got 3x squared plus 3y squared dy dx minus 9y minus 9x dy dx equals 0. I'm going to add 9y both sides. So I'm going to get rid of everything that does not have a dy dx in it. Subtract 3x squared both sides. and then I'm going to take a dy dx out of each of these two terms. So I have dy dx 3y squared minus 9x. Over here I've got 9y minus 3x squared. And then I'm going to divide by 3y squared minus 9x. What's an x? And I'm up here. Dy dx is, and I'm going to take a 3 out. Out of each of those, because I see that I can cancel. Alright, there's my dy dx. 3y minus x squared, there's my derivative, over y squared minus 3x. So this will give me the slope of the tangent line at any point that I want. 3y minus x squared over y squared minus 3x. So, part A, let's find the tangent. Find the equation of the tangent line. So this was part A. Well, actually, part A was to verify the points on there. Part B, the tangent at 2, 4. Okay, there's my xy. Well, what's the slope there? Well, let's plug it into dy dx. 3 times y minus x squared over y squared minus 3 times x. So it looks like we got, what was that, 12 minus... So we got 4/5 for our derivative. So then we have the point, and now we got the slope, right? Here's our point, here's our slope, so y minus y1 equals m x minus x1. So y ends up being, what is that, 4/5 x plus 12/5. Okay, that's the equation of the tangent line at 2, 4. Now, I'm out of room here. Let me erase a little bit. So let's do, you know what, let me punch that in so you can see that on test. 4/5 x plus 12/5. See the tangent. Y equals 4/5 x plus 12/5. And you see that there's our tangent line right there at 2, 4, right? There's the tangent line. Now I'm going to get the normal or the orthogonal at 2, 4. So the line that's perpendicular to the tangent. Well, if this slope is 4/5, the slope of the perpendicular line, since their product's -1, it would be, I flip it over and change the sign, so its slope would be -5. So the, make sure I got my, the normal or orthogonal, which is perpendicular to the tangent. So the tangent had a slope that was 4/5. So the perpendicular slope would be -5/4. And we want it at the point 2, 4. So y minus y1 equals m, x minus x1, y minus 4 equals -5/4 x minus 2. Let's see, that'll be -5/4 x. Add 4 was to 10/4, so 13 halves. -5/4 x plus 13 halves. And you see it there in black. There's our perpendicular. Okay? Well, thank you so much for watching. That's it for today. There's a nice little picture as well with the normal as well as the tangent. Again, requiring implicit differentiation. You guys have a wonderful day.